slide.
Okay, perfect.
Okay.
So, well, sounds getting ready.
Yep.
If you don't mind, maybe we wait for just a couple of minutes in case some other participants gets in, and then we can start.
Okay, sure.
Thanks. Okay, maybe we can start now. So welcome everybody. It's my pleasure to introduce for today's talk Nicole Lemire from Western Ontario University, and she will tell us about codimension 2 cycles of classifying spaces of low-dimensional algebraic tori.
Okay, thank you very much. And particularly thank you to Ivan Cheltsov, who asked me to give this talk, and to Adrian for hosting, or hosting in some sense, because we've been having trouble with hosting. But anyways, so I will, and also, of course, I need to say that all this work is joint with Sasha Neshetov, and I will make it very clear what the big job that he did. Yes. So just some notation. So we're going to be working over field. KS is a separable closure, and my gamma K is the absolute Galois group. And Totaro defined the chowering of BG for the classifying space for an algebraic group. And in some sense, he made some sort of an approximation. So, so we take if you have a G representation and a closed G invariant subset, subscheme rather. We want to say that we can choose such a representation and such a closed G invariant subscheme such that G acts freely on the complement, and the codimension of S and V is greater than or equal to I+1. And then the neat construction that he had was that he defined it this way, because now this quotient is defined because of the free action. And so that those are the codimension 1 cycles. And then we define the total ring in the usual way. And so now we have got a commutative ring. And of course, lots of people have studied these nice rings. So here are the names so that I don't forget. So basically for split algebraic K groups, there's been a lot of work done. So of course, it's very natural to look at the classical groups. So Totaro looked at GLN, SLN, SP2N, and Totaro, and I can never pronounce his name, Pandarapandi, looked at ON and SO2N plus 1. And Rebecca Field looked at SO2N. Yukita looked at G2. Visozi looked at PGL3. And Vistali at PGLP additively. And so with all this work done, the question is, what about the non-split case? And of course, one can look at if you're going to look at the non-split case of anything, you should look at the non-split case of something in which you really do understand the split case. And with a torus, at least it's as simple as you can really get. So with a split torus, the Chow ring of BT is just sim of the character lattice. And so then this is a polynomial ring, and then our variables, sorry. So in particular, it's torsion-free. If you have an algebraic K-torus, then that means that that over the separable closure, it really does look like a split torus. And then there's the natural map that comes from base change to the algebraic closure. And this is a standard sort of thing with codimension 2 Chow groups. You look at this map and you look at this comparison map and you say, what can you say? And the problem is that the map is not either injective or surjective in general. However, in this case, as in other cases, this is the case for, because the codimension to because the Chow group is torsion free, then you can say that this is the kernel of this map. The torsion subgroup is this kernel. So the comparison does you some good. Okay, so Blinstein and Makaryev studied this quite a bit, the codimension to BT, the torsion part of codimension to BT. Well, in particular, they described it as the kernel of a short exact sequence. And they found out that, well, of course, it's an abelian group, but it's finite into torsion. And they computed a bunch of families of examples of these groups for algebraic tori that were nice. And I will say more about these examples later. But basically what happened was, in all the nice examples that they worked out, they found that this group was trivial. And so the natural question is, can you find, is there AT and a field that, oops, such that this is non-trivial. Okay, so most likely you guys are all experts on this, but just for a quick review on lattice torus correspondence, because it explains a lot of things that we're talking about here. So if you have an algebraic tori of dimension R, up to isomorphism, they can be classified as the finite subgroups of GLRZ up to conjugacy. And how does that work, or why does that work? Well, basically, the reason is that you can take such a torus and then you can look at this. Because, what is this? This is, oops, that's not right. Whenever you're trying to figure out what the isomorphism classes of K-forms of a nice object are, and the nice object happens to be quasi-projective, sorry, then you can index them by the Galois cohomology group with coefficients in the automorphism group of the nice object. And of course, it's also nice when the nice object has a nice automorphism group, and it does. So then this is, and also this group acts trivially on that one. So then we end up with this. And the image of such a homomorphism would be a finite group, and then you're all set. So that is very nice. And so you can look at this in the on the finite level as well. If you have an algebraic K-torus, there exists a Galois extension that splits it. So of course that means splits means that when I tensor over L, or when I base change to L, I get this for some R. If I have an algebraic K-torus that's split by, oops, what happened? I don't know what happened.
You got disconnected or what?
It says sick of the 40-minute time limit. I'm not on, that's weird.
That's really weird.
I've never had that experience. I mean, I'm always using the university Zoom license.
Okay, seems.
Is it back? That's, I've never.
It was back for a second.
So I'm not restricted to the 40-minute time limit.
No, there shouldn't be anything like that either here. Okay.
No idea why that happened. Sorry about that.
No.
Okay. So as I was saying, so there's this correspondence, and so we can have such an algebraic tori. And how do you make the G lattice? Well, you just take the character lattice. And how do you go the other way? If you had a G lattice, you can go the other way by taking group algebra, taking fixed points, and looking at spec. So that's the affine algebra, or the affine ring. Okay, So co-Flask resolutions are going to be important in this discussion. So we should have a quick review of that, although most people have probably heard of it. So Colio, Telaine, and Sansuc created these co-Flask resolutions, although their construction was geometric, which I'll allude to later. This is the integral representation theory point of view. So if you have a G lattice, it always has a co-Flask resolution. And what is that? It's just a short exact sequence of G lattices where this guy is G permutation. And this guy is G co-Flask. And what does that mean? That means that, and this is the thing that's hard to check, that the first cohomology group, with coefficients in n is 0 for all subgroups. And then, yeah, I said it was a short exact sequence of G lattices. So all these modules are free Boolean finally generated group, Z to the n's. Okay, so the n in the sequence, the co-Flask lattice in the sequence is determined up to stable equivalence, which means that if I had another such resolution for the same lattice, then I'd get the nice property that this guy and the other guy, the two co-Flask guys, are related in this way, where this is a permutation. And this is called stable equivalent. Okay, so and dually, because you can just take the Z dual of all this and then get Flask resolutions. So just very quickly, this is permutation. This one is G Flask, which means the same thing, except with take cohomology minus coefficients. So these cohomology groups are going to be vanishing for all subgroups. And yeah, and then it's a short exact sequence of G lattices. And what else? Then it's determined up to stable equivalence. In the same way. I won't go into that. Okay, so if you've got your G lattice, you've got a G Flask resolution. And the thing about this and why everybody likes them so much is that in terms of the torus, this tells you a lot about at least stable birational invariance of the torus. And there was a lot of work done on this. So if you have such a resolution and now you apply it to the setup of an algebraic torus split by some Galois extension with Galois group G, then what are you going to apply this to? You're going to take M to be the character lattice over L, and then you're all set. This is the G lattice, and so now there are these nice conditions. The torus is stably rational if and only if this F is stably permutation. So that means that, and these guys are both permutation. And that was due to Miata, and Saltman proved that if you have the same setup, so T is retract rational, and that basically means that it factors through, there's rational maps that factor through affine space. And that's the case if and only if, when you look at that F guy and you find that he is invertible, so there's some other lattice such that this is permutation. And then much more recently, Merkuriev and Scavia, Merkuriev, I think, introduced the notion of P retract rationality for a prime P, and Scavia proved this this criterion that this it means that this is P invertible. And what is this? Did I get that right? Just a second. Sorry. And this is dominant of degree prime to P. And P invertible effectively means that I can invert the prime and get that same statement. So after localization, it's a direct summand of the permutation. Okay, so this arose originally as constructed geometrically by Kolyutil and Sansuk and Voskresensky. I'm never quite sure who did what, which did what first, but then this construction was made very geometrically. So if you have, at least in characteristic 0, if you have an algebraic K-torus and you have a splitting field, so the usual setup that I've been talking about, but now you insist that you have a smooth projective model of T, then you can actually geometrically get a sequence that's a Flask resolution. And it looks like this. And the Flask module comes from the Picard group of the smooth projective model base changed L, and this is permutation, and it's generated by the components of the difference of these two guys. And so that's pretty nice. Now, of course, that it takes some work to do such geometric construction. There is an easier way to find these co-Flask resolutions. There's an easy, relatively easy algorithm to figure out a co-Flask resolution. The problem is that it's hard to prove that you have such a thing because you have to check so many conjugacy classes as subgroups. So not many examples are actually known. except that more recently, or well, it's been a while now, maybe 2012, Hoshi and Yamasaki did some amazing work implementing this algorithm and proving a whole lot of things about stable rationality properties of algebraic tori and low dimensions for dimensions less than or equal to 5. So that at least is good for the small dimensions. Okay, so now back to the original story about the Chow ring of BT. We want to look at Markariev's construction. So he made a very nice invariant that was purely in terms of integral representation theory to measure whether this torsion group or to determine the torsion group to a certain extent, or at least to measure whether it's non-trivial or not. So here's a straightforward construction. If you take a G lattice, you can embed it into this gamma to M, which is basically the quotient of the second tensor power of I didn't want to write that, of M with itself, modding out these tensors. And this one is just the second exterior power of the module, or the lattice. And these maps in the exact sequence are very natural. This just goes to what they the class of M tensor M in this module, and this guy just goes to its friend in the second exterior power, and this is a short exact sequence. And what is this? This is the connecting homomorphism. Okay, so quite there yet, but just to remind you of, okay, so we've got this nice sequence, and we've got the connecting homomorphism in cohomology. And so then we need to look at some properties that are actually fairly transparent. Obviously in this game, we need to know what happens with permutation modules. You can write down an explicit splitting of that sequence in the case when M is equal to a permutation lattice. And I'm not going to write it down, but anyways, this splits in that case. And then that means that this is trivial. So of course its image is trivial. If M is isomorphic to a Dirac sum, so it's decomposable, then the image of this commutes with images. Which is a nice property. And that, if you think about these two statements, if these guys are stably equivalent, then you get that these guys are the images are isomorphic. And that's all set up. These properties are all set up in a very nice way to make this definition make sense. So what he's going to do is he's going to define this to be if you've got a G lattice, you define this to be the image of alpha n for the coflask lattice in the resolution. And the way we've set it up, then because of this, the fact that stably equivalent lattices have the same image, this is well defined. And if M is too invertible, no, sorry, if N is too invertible, rather, then this is trivial. It's also easy to see from this description because this group here is to torsion, that this is true. And you can also show the finiteness. The restriction map to the CLID2 subgroup is injective. And direct sums work well. Okay, so now Merkuryev did all this setup, and here's the point. If you have an algebraic K-torus with the splitting field and the algebraic and the Galois group of the splitting field, then what happens is this is a quotient of this guy. Which is nice because then if this is non-zero, then the other one is. So then the other thing is it's on the nose, correct, if we take a G representation that's faithful, QG representation that's faithful, and we take the fixed field, and then we've got a G-Galois extension. So in this case, these actually coincide. Okay, so that's great. As I promised before, we're going to get back to Blinstein and Mercurius examples. I didn't want to, yeah, okay. So I will talk through these. I didn't want to have this all there. So if the dual of the torus is 2 retract rational, then something is wrong. Did I have that right? No, that's okay. So the character lattice is 2 invertible, then it's trivial. And then in the case of a torus of this form, where this is the V restriction of a Galois extension, the split torus. An easier way to say that is that its dual torus is the norm 1 torus for a Galois extension. And the other thing that you can, from a representation theory point of view, you can say that the character lattice of such a thing is just the augmentation ideal of the group ring, of the full group ring. And so basically he showed that that was trivial in that case. And they also showed, because of the reduction to CO2 subgroups, they showed that it's going to be trivial in the case when G is cyclic, because all coflask modules in that case are invertible. And in the case of the Klein 4 group, it's understood what the coflask lattices look like. So again, they could get this triviality. So those are all their nice examples. And actually they had, Mercury also had another very nice example that I just didn't want to cover here. Now, Scavia, having heard their question, produced an amazing example where this invariant was non-trivial. And in his case, what he did was that he took, the example that he took was the CO2 subgroup of the Suzuki group, the Suzuki 8, and that's a group of order 64. And the rank of the module that he constructed is rather large. But his construction is very amazing, because what he did, instead of trying to compute one example at a time, he basically looked at a family of examples in which you could find in which the coflask resolutions were essentially known due to the construction. And then what he did with that is he took that construction and rephrased the problem in terms of low term a group cohomology with coefficients in Z mod 2. And then after having rephrased the problem, in the sense that he showed that this invariant would be non-zero if some conditions were true about the group cohomology with coefficients in Z mod 2, and then looked for an example that fit that bill, which is very amazing. So the of course, there's one issue here, is that the example is very large. So so then we were looking at the low dimensional algebraic tori. And actually, I had heard Makarev's talk earlier, before I heard Scavia's result, and I started thinking that was a pretty nice thing to look at from the point of view of low dimensional tori. And so now I'll just explain what we did. So just for notational reasons, if you have a finite subgroup of GLNZ up to conjugacy, then of course there's a lattice that it acts on, and I'm going to denote the G lattice as mg. So up to conjugacy, the G lattice that the group acts on is determined up to ZG isomorphism. Okay, so here is an observation of Serre. I'm actually not totally sure whether this result is due to Serre or was whether it was. I found this in a paper of Serre. But it is actually in an exercise, so I wasn't totally clear on the attribution. So what the thing is that in GLNQ, one can look at the two groups, and there's like a CELO theorem working out here. So there is a unique maximal two group up to conjugacy for GLNQ. It can be defined recursively. I mean, with a recursive formula, which I could write down, but I'll skip that part. But the point is that if you look at the formula, a way of interpreting it is that this is the CELO2 subgroup. Of the Weil group of Bn, acting on QBn, the Bn root system. So this is in particular a sign permutation action because the Weil group of Bn acts by permutations and sign changes on the root lattice for Bn. So this has the following implication for two groups of GLNZ. Well, of course, it's not quite as good as it is in the rational case, but it does tell you some information. Oh, so I should say, so that's the maximal group up to conjugacy. So if I have any other two group in GLNQ, I know that it's conjugate to a subgroup of this guy with that action. So that means that if I have a two group that's a subgroup of GLNZ, then at least one can say that this guy is sign permutation up to Q, I mean over Q. So that doesn't mean that it's true integrally. So what it does mean this. Where I'm thinking of G embedded in this CELO2 subgroup of WBN. Okay, so just a quick observation. The thing that's nice about root systems is that if you had a lattice for the Weil group of a root system, or if you think about just a reflection action on a reflection space, you have control over what the possible Z forms are of this QG vector space. And it turns out that it must be the case that such a lattice must be trapped between the root lattice and the weight lattice of the root system. And so this is not the answer in terms of the two groups, but this is at least giving you some information that for the vial group of BN, so something acting on permutations and sign changes on QBN, the possible lattices would be these guys up to isomorphism, and in low degrees, they might coincide. So what is going on here? For n is less than or equal to 5, if you have a 2 group, one can see that this lattice as a G lattice, which is sitting inside and it's embedding in the vial group of Bn, it's a direct sum of lattices of the above type. It's even better than that, but it gets more detailed, so I just will quickly show you this. So in n is equal to 2, it's very easy. The only possible, I'm talking about the maximal 2 group and its associated lattice. And so then the group that I'm talking about here is the COO2 subgroup of the vial group. But the point here, regardless of the details, is that the only direct sums that occur are the root lattice of Bn, the weight lattice of Bn, and the root lattice of Cn, but only in dimension 5. And there are some issues with decomposability, but you still get only those ones. So in the case of the root lattice of Bn, I can produce a co-Flask resolution for the vial group of Bn and prove that that is a co-Flask resolution. It's not always the case that you have a family of co-Flask resolutions. So using that information, we could make some reductions in the low dimensional cases, and we're able to make the computations easier in that sense. So what were the reductions? Well, we can assume that this is a 2 group. We've already seen that. We can assume that the associated lattice is G indecomposable. And the point about Bn is that it's sign permutation. So in particular, its co-Flask resolution has a co-Flask lattice that's permutation. This is very easy to see. It's like one of the very nice resolution. Actually, I can write it down, that you can get. Oops, that's n-1. Oops. Did I make myself? Oh, I thought I could write it down. Well, this is a permutation. I'm screwing that up. Oh, wait a second. Okay, maybe I shouldn't write it down. Sorry. It's easy to see that that's a permutation lattice. So sorry about that. So anyways, you can eliminate the sign permutation case. The associated torus is also rational. That's well known by various arguments. And what was I going to say? Oh, right, not sign permutation. So we can look at the lattices that have that are restrictions. If all these things are true in dimensions 3 and 4, the lattice would be, you could look at the lattice as the weight lattice for Bn, obviously just for n is equal to 3 and 4, restricted obviously to the group. And in the case of n is equal to 5, then you have to also consider this. So we made these reductions, and so that's what our starting point was. Actually, maybe not, maybe to here was the starting point. And so for n is equal to 3 and 4, what this meant that we had this analysis of what the lattice looked like is it meant that we only had one Coflask resolution to deal with. And you can always restrict to a Coflask resolution to a subgroup. You could possibly get a smaller resolution without doing it that way, but at least you have one. So that was something that we could do with n is equal to 3 and 4. It was enough to make the computations. So Sasha Neshatov did an amazing job on these computations. I didn't believe it was going to work out like this, but it did. So first of all, he translated, and I didn't go into the details, but Merkuriev made his invariant. He expressed it. He showed a way in which you could express it all in terms of codimension 1. I mean H1 computations. And so Sasha used that idea and refined it somewhat so that he could compute it all in terms of H1 computations. So that was good. And so we found that they were all trivial. And I think Sasha was quite disappointed at that point. But so he decided to keep going and look at dimension 5. And so here we also produced, not as nice, but we produced a hands-on resolution for ZC5. And so we were able to proceed, but the computations got a lot worse. So he made some reductions, and he produced I won't go into the details, but just he made a variant of Mercuriev's variant. I mean, an invariant that was a mod 2 invariant that was a bit bigger, and so this meant that if he was able to show that the mod 2 invariant was 0, which was true in most of the cases, then the integral one would vanish. And he still did have to work out some cases, a smaller number of cases that need to be dealt with integrally. Okay, so at this point, we also found out that everything was zero. So again, we were disappointed we put this away. And then we found out about Scavia's example, and then he was probably working on this at the same time, but we didn't know the chronology. But he produced this example, and we left it. And then we came back to this, and Sasha made made a really big advance in the computations, and made a technique to compute Smith normal forms over Z mod 2 to the n in order to make the computations feasible in dimension 6, because, well, the CoFlask resolutions were big, and the thing is that we're not just looking at the CoFlask lattice. You're looking at the second exterior power of the CoFlask lattice, so the ranks are getting quite large. Anyways, so in the end, we have 54 examples. This is what you produced with non-trivial invariant. Most of them are rank 1, but 3 are rank 2. And the other thing, from my point of view, the thing was interesting is that this observation that I had made seems to fail in dimension 6. That is, that the maximal subgroups, the maximal 2 groups in dimension 6 are not necessarily, although they are in most of the cases, restrictions of root lattices to the CLO2 subgroup, the subgroup of the CLO2 subgroup, but they can be, there are other possibilities. And here is one example of the ones that we had, and this is the caret code. The group is of size 8, so it would be minimal. And the lattice, which is not isomorphic to any of those lattices that I talked about before, has a nice description. It's just, so these guys are plus or minus 1. So it's just this, the span of vectors that are all 1s and minuses 1s, but the product of them are 1. And that is all I have to say.
Well, we can all unmute, and thanks, Nicole, for a nice talk. Thank you. So now it's time for questions. I have maybe a naive question. So what is so specific to dimension 6? I mean, the group looks quite small and the lat is very natural.
Yeah, it's, well, to be honest, we don't have a total explanation about that. It's strange. Yeah.
And
so actually our counterexamples that he came up with, the largest one is of order 64. The group is of order 64. 2024. Of course, they're all two groups. And just for context, the maximal, this CLO2 subgroup of the vial group of BN, that's of order 2 to the 10. So 10, 24. So they're not maximal groups for some reason. I haven't investigated what all this, I mean, he produced this, but I'd like to understand what's going on. That's interesting from that point of view. But the computations are quite, they're quite massive because of huge coflask resolution. So one possibility is that one could reduce. I think that, I should have said, did I not say? I hope I did say. In dimensions up to 5, we used our own resolutions, but for n is equal to 6, he used Hoshi and Yamasaki's algorithms to find the coflask resolutions, because we didn't really have an idea, but it would be interesting to understand what's going on there, and to get the one thing that, I mean, many invariants in this sort of racket depend on these coflask resolutions, but there aren't that many families that are known in a nice way, like where you can construct them and say, okay, here's a family of such things, because you need control over the conjugacy classes of subgroups, information like that, which isn't so easy if the group is large.
Thanks. Any other question, comment?
You misplaced your camera. Oh dear. I don't know how you can misplace it, but anyways.
So if no further comment, let's thank Nicole again. Thank you. You can stop recording if you don't mind.
Yeah, great. I forgot about that. It's very funny.
Yeah, so sorry for
actually
putting on you or the tasks.
From the iPad before. I always recorded the other way. So, okay, did I stop?